Hello. Hello. Good afternoon, everyone. Welcome to today's talk on Markov chains and stochastic process by Sarvesh Iyer. He is a fourth year SRF at ISA Bangalore. His main interests include control Markov chain and Harnack inequalities for Levy processes, along with stochastic differential equations. So you are requested to keep yourselves mute. In case you have any questions, you can unmute yourselves to ask, or you can put it in the chat. So without any further ado, let's start.
Am I audible?
Yeah.
Okay. Can you hand over Spotlight to a user called Presentation?
Okay.
Because that's where the presentation is. Yeah.
I don't know. It's not allowing for Spotlight actually.
Okay. Just give me a second. I'll see if I can configure something.
I guess for that it needs the video to be on or something like that.
Yeah. 1 second. I'm just trying to share my screen. And it should be coming in sometime. Yeah. Right. I hope my screen is visible, at least in its entirety. So thank you very much to the MAT Club for giving me this opportunity to present some of my research observations in front of an audience of roughly 20 people, which is very nice. So hello and welcome to this talk on stochastic processes and Markov chains. My name is Sarvesh Ravichandran Iyer. Today is the 2nd of April 2022, which I had written as the 3rd, and I corrected it just 10 minutes before this talk. So without further ado, let's get into this talk. This talk is basically supposed to be an extension of probabilistic notions. So it would fall under the mathematical branch that is probability theory. But for the purposes of this talk, we will restrict ourselves to certain prerequisites, to topics that can be fulfilled by certain very basic prerequisites that I will be discussing next. So the following prerequisites will be necessary for you to enjoy this talk. For probability, I would urge you to at least have knowledge of everything up till notions of convergence. So you have the notions of convergence in probability, convergence in distribution, convergence in mean, and convergence almost surely. So these 4 notions of convergence that are there, maybe not the notion of mean convergence, but the other 3 you should technically have an idea of. So, and everything before that. So that would include sample spaces, that would include joint distributions, distribution functions, and everything. Right. So if you're talking about analysis, ideally Riemann integration and fundamental theorem of calculus should be enough. So I will not be using too much analysis in this talk. Other basics, well, everything in your first semester of BMath. So a little bit of group theory will be used, a little bit of algebra may be used. But apart from that, I don't think I will be using anything without introducing it. So if I use certain concepts from linear algebra, differential equations, and higher algebra, these will be introduced ad hoc. In other words, I will introduce the required definitions and talk more about them when I'm introducing them, so that I can keep my audience informed rather than assuming that they know what I'm talking about. And of course, the last thing that you need is a sense of humor and a way of keeping yourself alert. This is going to be a huge talk, about 1 hour, 1.5 hours. So I wouldn't mind if the host of this meeting informed me at some kind of halfway point, so that we could have like a 5-minute break, so that people can recharge themselves in that break if necessary. That is, of course, if they feel the need to, have a break. Otherwise, I'm fine going through this. Right. So please make sure you have a sense of humor, because I will try at times to make certain connections that may sound implausible or some kind of mathematical jokes. That's just to keep the momentum of the talk flowing. So I hope that these will be appreciated. Right. So without further ado, the aim of the talk is to demonstrate the ubiquity and mathematical quality of stochastic processes and Markov chains. In particular, what do I mean by the word ubiquity? Anything is said to be ubiquitous if it's present everywhere. So for example, they say God is ubiquitous, right? So I'm trying to make a point via this talk that stochastic processes and Markov chains are present pretty much everywhere. Mathematical, non-mathematical, any area of science, you may find an application of stochastic processes and Markov chains. Furthermore, these are genuine pieces of mathematical quality in the sense that when you understand the design behind stochastic processes and Markov chains, you will understand why mathematically they are studyable, or one can explore them and create definitions and results based on these topics in ways that are very natural and not very artificial, right? So I will now be motivating stochastic processes as a concept. So, okay, hang on. Before that, some notations. So these notations are just to make sure that I'm, in sync with everybody's first year probability days, right? So omega is a countable sample space, and small omega in big omega is a typical sample element. So sometimes when I say small omega, big omega, that's a very long phrase. So sometimes I might call small omega as W because of the resemblance of the letter, right? So P from omega to 0,1, small p that is a PMF. So any kind of PMF will be represented by small p ideally. So random variables on omega will be represented by capital letters which are coming towards the end of the alphabet. So W, X, Y, Z, and so on, popularly X and Y. Events will be denoted by earlier letters of the alphabet and this letter E with an index. So A, B, E, I, or D, or something like that, right? So then you have two kinds of sets, I and S. So I is typically an interval. So for example, it could be 0, 1, or it could be 1, 2, 3. So it could be the natural number, something like that. Whereas S could be any set. So S could have numbers, it could have functions, it could have shapes, it could have all kinds of paths, or it could have CID episodes. Well, CID episodes, as we will see later, because that's important. So P and E, which are the stylish P and E, so to speak, these will be used for the probability of an event and the expectation of a random variable respectively. Right. Okay, yeah, right. So, and there's one more notation that I need to add here. That is the following notation. It's the indicator random variable. So the indicator of a set A is defined for all, well, omega in omega, if you like. So I should be using omega here. So it's defined as 1 if omega is in A, and 0 if omega is not in A. Right. Please let me know, somebody, if the writing is not visible. I think it's visible to me at least, so I hope it's visible to everybody else. Right. So this indicator random variable is very important for us because, as it turns out, we will be using it for certain concepts in Markov chains. Right. So we will now move to the next slide where I will motivate stochastic processes. So why do we study stochastic processes? We study stochastic processes because there is a need to understand a set of random variables as a collection with structure. So if you think about a group or a vector space, it isn't just a bunch of elements, right? It's a bunch of elements that are related to each other. So for example, a group is a set with a binary operation. It's a set with an identity. It's a set where each element has a unique inverse, okay, an inverse if you like. So those are sets with structure. They aren't just elements bunched together, right? Similarly, vector spaces, there's an operation of addition, there's an operation of scalar multiplication, or maybe you could look at an organized library. An organized library is a place where books aren't just randomly stored next to each other. They're stored in such a way that they're easy to find. You can easily find books, you can easily retrieve books, or you can think of a sorted array, for example, where, if it's sorted up, then you have an idea of where to look for an element, say using a binary search. So the need to understand a set of random variables as a collection with structure is the idea of a stochastic process. So a stochastic process bunches random variables together with the idea that we can collectively study them and classify them. Right. The next thing is to model progressive randomness. So randomness per se is a property of the underlying sample space, right? So you have a sample space, you have an associated probability measure on it, probability distribution, if you like, a PMF. And what we do here is when we consider a bunch of random variables, we order them in a certain way that there is a progressive randomness that develops across the change in an index set, such as space or time. So for example, let us say you are looking at flipping coins at different times of the day. So if you are flipping coins at different times of the day, then in some sense, the amount of randomness that's involved in flipping one coin is less than the amount of randomness that's involved in flipping, say, 10 coins. There's far more randomness involved there, right? Similarly, if you look at random chance games of chance and gambling, if you're gambling, it may be easy to predict how far, it may be easy to predict your outcomes at the end of one gamble. So if I roll one pair of dice, I know that, I can get only, or rather not one pair of dice, just one dice maybe. I know that I can get only values between 1 and 6, and with probabilities, say 1/6 each. But what happens when I roll 15 dice each? Well, the probabilities just get convoluted. They just get very difficult to distinguish. So modeling progressive randomness is the idea behind introduction of a stochastic process. So there are two more examples that I give here: modeling the spread of a pandemic with time and modeling a social network like Facebook. These I will expand on more. So the basic idea of both is that you have something developing randomly with the idea that the amount of randomness is sort of increasing across an index set, such as space or time. And the third is modeling information flow across random variables using the index set. So you have an underlying index set, which is basically speaking used to provide structure to this set of random variables. Now what happens is that the index set has certain interactions that go on with it. So for example, if you take an index set like 1, 2, 3, 4, then 1 is less than 2, which is less than 3, which is less than 4. Therefore, a natural ordering amongst the index set elements transfers to a natural ordering amongst the stochastic process elements. That is to say the random variables, x1, x2, x3, x4, for example. So this allows us to introduce natural interactions and dependence among these random variables. So therefore, we can talk about dependent random variables, and we can structure the dependence using the index set. Furthermore, we can also allow careful user interference in this information flow. So the reason why this is called information flow is because there is certain information that is captured in the index set. So for example, if you look at 1, 2, 3, 4, there is an order that is captured. If you look at say 0, 1, that is to say the interval 0, 1, there is an order there as well. So that is information flow on the index set. And the idea is we want to transfer that to the random variables that will be involved in this stochastic process. Furthermore, finally, last but not the least, long-term effects can be studied using limit theorems. So we can introduce limit theorems provided our index set is sort of large enough or is going to infinity in some sense, and we can study long-term effects or the distance or the relationship between stochastic processes that may apparently be very far apart as far as the index set is concerned. So without further ado, now we move to the definition of stochastic processes. So a stochastic process is it's an extremely generic definition. You just have any index set I, and a stochastic process with index set I is a collection of random variables that are on a common sample space. So you have one single probability space, which is omega comma p, and a stochastic process is just a collection of random variables xi, I and I. So it's basically an indexed set of random variables. That's it. That's all it is. The reason why it's called a process is because typically I is an ordered set. So either it's 0 infinity or it's n union 0. So natural numbers may or may not include 0. In my case, I'm choosing it to not include 0. So that's why I say n union 0, right? I'm starting from 0 for the benefit of some computer scientists in our crowd. So a stochastic process on I prime, which will be used to denote n union 0, is called as a discrete stochastic process. So, or rather a discrete time stochastic process. Somebody is unmuted.
Huh? Math club.
So a discrete time stochastic process is one that operates on the following index set, n union 0. So we restrict our attention to such processes for the purpose of this talk, because it's possible to choose 0 infinity, which would be a so-called continuous time process. However, the technicalities behind such processes is just far too deep, and we do not have the prerequisites to cover that. Right, so the key idea here is to think of I prime as time. So if you have a stochastic process that's indexed by I prime, it models randomness with time, and therefore we are allowed to introduce time-dependent interaction in a stochastic process and talk about limits in time. So for example, if you have x1, x2, x3, and so on, one could talk, theoretically speaking, about the quote unquote limit n tends to infinity xn or something like that. So, or we could think of x1 as what happened at time 1, x2 as what happened at time 2, x3 as what happened at time 3, right? So that's the idea behind a stochastic process's definition. So we will be sticking to discrete time stochastic processes. Continuous time stochastic processes, I'll speak very little about them at the end. Right. So now we will talk about an interpretation of stochastic processes as random paths. So what we do for this is let capital omega.
Go back to the previous slide once.
Yeah. If you want to write down things from the slide, right? In the chat, I've attached the entire slide. I have attached all the slides, and I've attached, I've just written a message saying I've attached all the slides. So you need not bother me about copying from the text, for example. Right, are you done?
Yes, thank you.
Yeah, welcome.
There's something also known as a continuous time, like discrete is there.
Yes. So, somebody is asking me to send the slides once more. So I'll just do that. But until then, I'll just do that. Yeah, just a second. So if I is 0, infinity, so that is to say, if this guy here is being considered as the index set, then you call it as a continuous time stochastic process. So continuous time stochastic processes are very difficult to study, because the problem with continuous time stochastic processes is that you cannot talk about stuff like what happens between neighbors and things like that. So the transition from one sort of time point to another time point is, when it becomes continuous, it becomes you can't really do it unless there is an underlying relationship between the xt's, where t is in 0, infinity, which is sort of very natural. So for example, continuous paths or right continuous paths, you can't do it unless you are kind of this thing. Yeah, thank you, Pragnadipto. He has shared the link, so everybody can take a look at it. And this talk will be very text heavy, so I'm pretty much everything that I say is there in the slide in some sense, right? So we will now move to the random path interpretation, right? So what is this random path interpretation? You fix your W in omega, and you look at the mathematical object that is given by taking all the xi of omega and just concatenating them together in the order given by the n union 0, in the order as per I prime, so the order of the natural numbers, right? By the way, I should be starting from x0. So I've made a small error here. I should be starting from x0 here, not x1. So there should be an x0 of omega here. So once there is an x0 of omega there, then essentially speaking, this object x is a function from omega to the set of all functions from I prime to s. Because if you look at the definition, if you call x of omega as f, then f is defined as f of I is equal to xi of omega for all omega, for all w in omega, and for all I in I prime. So once you think of this interpretation, every f from I prime to s can be thought of as a path in s. Why? So because at different times, one is moving to different elements of s as dictated by f. So just to give you an example, if I'm watching CID episodes, if at time 1, I'm watching CID episode 490, and if at time 2, I'm watching CID episode 492, and if at time 3, I'm watching CID episode 1500, then I'm using 490, 492, 1500 as a tuple, and that itself has resulted from a single unit of randomness. So for a single sample point, I have got this entire path. So I've got this entire bunch of CID episodes that I've seen, right? And that's why stochastic processes can be thought of as a random path in an appropriate state space S, where the state space can be anything. So I just spoke about CID episodes, but they could be pretty much anything, right? So in that case, the mathematical object X is called as an S-valued stochastic process. So that is basically saying that each Xi is taking values in S. So the random path interpretation allows us to study instances of progressive randomness. So why is that? Well, that's because I think I should have a slide for explanation at this point. That's right. So this is a slide that I give myself for writing. It's just very helpful because it's just a clean screen, so I can write as big as I want. So let's say you have omega 1, let's say, and omega 2. So these are two different guys, which are both in omega, let's say, both in capital omega. So you have x1 of omega 1 and x1 of omega 2. You have x2 of omega 1, x2 of omega 2, x3 of omega 1, x3 of omega 2. Now, if I did not think of this as a stochastic process, but I just looked at each of x1, x2, x3, etc. as separate random variables, that is to say, not as a collection, then I might be more logical. It might be more logical of me to think of these boxes as units. So each box contains x1 of some omega. So I'm just studying that particular random variable when I'm restricting myself to a blue box. So for example, the first blue box is x1, the second blue box is x2, and the third blue box is x3. So focusing my attention on one box fixes my attention to that particular random variable. Now the pathwise interpretation tells me to not fix my attention to a particular random variable, but to fix my attention to a particular sample element. That is to say, instead of looking at these guys, I look at the horizontal boxes that are like this. So I hope you can see the green boxes here. These green boxes, by the way, this will continue on to x4, x5, and so on. So I'm just putting the dot, dot, dot to indicate that. These green boxes would be a so-called pathwise interpretation. So that is what I'm kind of telling you guys is important in a stochastic process. So it's very important to sometimes think in pathwise terms. Right. So we will now move to some examples of a stochastic process. Oh yes, before that, let me talk about something called as a Borel-Cantelli lemma. So the Borel-Cantelli lemma is the fundamental link between individual random variables and stochastic process related events, right? So let's look at the first line here. If you look at the first line here, these events that you see here, omega xi of omega in ai, they are events that are dependent only upon xi. So that is to say, each event, you can understand whether each event has occurred or not once you see whether the particular xi has been observed or not. So if x3 has been observed, then you will know if the event omega such that x3 of omega is in A3 is true or not. So this summation on the top is essentially speaking a summation of events involving individual random variables in some sense. This guy, on the other hand, on the bottom, this guy that you see over here is a stochastic process related probability. So it's a stochastic process related event because it combines all of them and it says what is the probability that xi of omega belongs to ai for infinitely many I. So we're no more looking at one I. We're looking at all the I put together and we're asking, are there infinitely many I for which this is true? And the remarkable thing about the Borel-Cantelli lemma is that one can relate the individual probabilities of these events occurring to the probability that infinitely many of those events occur, which is a stochastic process related event, using these two Borel-Cantelli lemmas. So the first Borel-Cantelli lemma is for all kinds of events. And the second Borel-Cantelli lemma is for independent events. So that is to say, if the xi are independent random variables, then you can, under some conditions, assure yourself that a particular event relating to the stochastic process actually occurs with probability 1. So this is a frankly remarkable result, because this is the first bridge between stochastic process related events and individual random variable related events. And this also promotes the pathwise interpretation, because the thing that I have underlined in blue, it's essentially a property of the path that's related to omega. So if I fix an omega and I look at the path related to omega, the event xi of omega is in ai is true for infinitely many I is a function of that path. So that's why we are switching here from an individual interpretation to a pathwise interpretation. So technically speaking, this is like a switch from something involving the blue boxes to something involving the green boxes. So you can think of it as like a 90-degree shift in perspective, if you like. Right. So let's look at the simplest stochastic process.
What was that? Why did you write stochastic process on top of that probability?
Because that event, so let's look at that event. Oh, can you give an example of the lemma? Yeah, sure. I can give you an example of the lemma. Just hang on before that. So what is this event that you see here? This event that you see here is the event that xi of omega is an ai is true for infinitely many I. So that is to say, you have these events and they should occur for infinitely many I. So what is this guy a function of? So this guy is a function, that is to say, it is determined by the entire path related to omega. So you have to observe everything related to omega, x0 of omega, x1 of omega, x2 of omega, and so on, which is basically speaking the path associated to omega. So because this guy is a function of the path, the Borel-Cantelli lemma is basically transferring something relating to the individual random variables to something relating to a function of the path, which is fundamentally a stochastic process related notion. I hope that clarifies your concern. Yeah, right. So to give an example of the Borel-Cantelli lemma, one could do simple stuff. So for example, is a collection of AIs a stochastic process? No, a collection of AIs is just a collection of events. So stochastic process is a collection of random variables. So for example, if you take the indicators of the AI, those could form a stochastic process, but not the AI themselves. That's just an infinite collection of events and with almost no particular relation. Right. So let's give you an example of. So you can define the following stochastic process, right? So this stochastic process is defined as follows. You have xi of omega is equal to, let's say, I don't know, 1 by I, or rather, let's just take this. Let's just take a very simple situation, right? Let's just take 1 with probability 1 by n, and let's take 0 otherwise, something like that. Okay, so it's basically 1 with probability 1 by n, and it's 0 with probability, well, 1 minus 1 by n, if you like, which is basically, so to speak, 1 minus 1 by n. And furthermore, we declare all the xi as independent. So we declare the xi as independent random variables.
Is
Right.
n here what is n here?
Oh, sorry, I'm so sorry. Xn of omega, excuse me. Yeah, that just has to do with. And one more thing I should do is, because I'm starting counting from 0, I'll start my indexing from n plus 1. So let xn of omega be 1 with probability 1 by n plus 1, and let it be 0 with probability 1 minus 1 by n plus 1. and let them be independent random variables. So we can ask ourselves some questions. So the first question that we can ask ourselves is fundamentally stochastic process related, right? So for this guy, what is the probability that the summation I equal to 1 to say n xi is convergent? So what is the probability that if I sum all the xi's, it is a convergent sequence? So this is a fundamentally stochastic process related notion, because I'm combining all the xi's together and asking a single question relating to all of them. And this answer can be given using the second Borel-Cantor lemma. Because the xi are independent, all we need to do is check whether, so not that we need to check it. So how do you prove that this quantity actually equals 1? How do you prove that this quantity actually equals 1? You prove it by observing that the omega for which xn of omega is equal to 1, the probability of that event is equal to 1 by n plus 1, right? And that sum, when I sum it from say I equal to 1 to infinity, probability of omega, that
What are the sets? What are the sequence of subsets in this case?
Well, it's the AI would be 1. So it's just so AI is just 1 in every single case for all I here. So if AI is 1 in every case, I'm just asking myself if xn of omega is equal to 1, right? So now what is this summation I equal to 1 to infinity probability of omega such that xi of omega is equal to 1? It's just summation I equal to, okay, I should start from 0 technically. I equal to 0 to infinity 1 by I plus 1. But that's just a harmonic series which we know diverges. And therefore, using the Borel-Cantor lemma, the summation from I equal to 1 to n xi is almost surely heading to infinity. In other words, it's almost surely a divergent sequence. So I made an error here. So this is equal to 0 because it's almost surely divergent. So if it's divergent, that equals 1. And if it's convergent, that equals 0. So this is just a very toy and baby example of the Borel-Cantor lemma.
It doesn't depend on omega, right? What sample element is there?
No, it could. So the point is, no, what are you saying doesn't depend on omega?
The Borel-Cantor lemma.
The Borel-Cantor lemma does not depend upon omega. No, it doesn't depend upon omega. It doesn't depend upon omega. So the point is, it only depends upon the probabilities. Are those particular probabilities summable? If they're summable, then the probability that infinitely many of them is true, or infinitely many of those events, that is 0. If they are independent and if that sum is infinite, then it turns out that the probability that infinitely many of them occur is 1. And the point is, once I realize that infinitely many of the xn are equal to 1, that particular sum simply has to diverge because the sum of infinitely many ones is not going to converge. So that's the reason. That's just a very simple application of Borel-Cantor lemma. So I wasn't really planning to share this. The reason why I wasn't planning to share this is because the proof of the Borel-Cantor lemma is actually beyond everybody's this one. So I defined AI as 1 for all I. I have written that here. AI is defined as 1 for all I. Just the set 1. Just the set 1. So if something belongs in AI, it has to be equal to 1. That's the point. Right. By the way, there are some generalizations of Borel-Cantor lemma, but the Borel-Cantor lemma fundamentally it requires this one to prove. It requires measure theory to prove. Right. So we will now move to examples of stochastic processes. So the first such example is the IID Bernoulli process. I need to speed up a little, so I will try to do that. So well, P sum of xi convergent again. Yeah, sure, I'll do that. I'll do that. Right. So if you look at the probability of omega such that xi of omega is in ai, that guy is 1 by I plus 1. Right? Now, because that guy is 1 by I plus 1, that summation, that this particular summation here, summation I equal to 1 to infinity probability omega xi of omega is in ai, that is a divergent sequence. Because there's just an infinite sum, that's just a harmonic sum, right? Summation I equal to 0 to infinity 1 by I plus 1. So that diverges. Because that diverges, and because of the second Borel-Cantelli lemma, it's true that infinitely many of the xi are equal to 1. And because infinitely many of the xi are equal to 1, whenever that occurs, it's obvious that summation I equal to 1 to an xi cannot be convergent. Because if there are infinitely many ones, that particular sum is just going to have to be infinite. So the probability that sum is convergent actually equals 0, and the probability that it's divergent actually equals 1. Right. I hope that's clear. In case it's not, we can come back to it later. Yeah, thanks for the confirmation. Right. So we come to the most simplest kind of stochastic process here, and that's just an IID process, right? So the collection xi, which we just looked at. So what we looked at earlier was a collection of independent random variables, not identically distributed. So they weren't all having the same distribution, but they were independent, right? So the collection xi is an independent collection, and every xi has the same distribution. So this would model some very simple examples such as independent coin flips, different customer choices amongst product in a store, or how much people wait at a bus stop till they can get a bus. So independent coin flips can be thought of as independent Bernoulli random variables. Different customer choices amongst product in the store can be thought of independent multinomial random variables. How much people wait at a bus stop till they can get a bus can be thought of independent exponential random variables. So some vague questions that can be asked. So these are questions that I haven't phrased them mathematically yet, but I'll be quickly doing so in the next slide. So what is the largest run of heads? What is the waiting time until you see 3 consecutive tails? How long do I need to flip coins till I see three consecutive tails, for example? So what about the second situation? So what is the best chosen product? Was more Santur soap chosen, or was Mysore sandal soap chosen more, or was Lifebuoy chosen more because the kid on the Lifebuoy looks a bit attractive? What was the lowest chosen product? Probably the costliest one, Lux soap or something. How much do the waiting times vary? So are people, roughly speaking, waiting for the same amount of time at a bus stop till they can get a bus? Maybe some people are waiting too much, maybe some people are waiting too little, something like that, right? So those kind of stuff can be modeled and studied by IID processes. So we look only at the Bernoulli process because it turns out that the rest of the processes are well studied, but the methods to study them are not particularly attractive, right? So the Bernoulli process is just, you just have IID with each guy being 1 with probability P and 0 with probability 1 minus P. So that's just a Bernoulli P process because 1 is considered a success. So you're succeeding at each time with probability P. So this would model biased conflicts, right? The point here is that you guys already know a lot of answers to some questions concerning the Bernoulli process. So for example, what is the waiting time for the first one, or the first head, if you like? Well, that's just a geometric random variable because geometric random variables are meant to model, first success times. What about the number of ones in the first capital N trials? That's a binomial random variable because you're looking at the number of successes for a fixed number of trials. What about the waiting time of the first k ones or the first k heads? That's a negative binomial as a sum of independent geometric random variables. Now, here's a difficult question. So this, rigorously speaking, I have defined this quantity, capital Rn here. And let me give you an idea of what it means. So let's say you have a run of zeros and ones, right? So you have, let's say 0, 1, 1, 0, 0, 1. Okay, the way I'm saying it, I'm not writing it 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, suppose 0, 0. Right. So this would be 21. So this would be n equal to 21 tosses. And what I'm looking for is the largest number of consecutive ones, right? So on this occasion, the largest number of consecutive ones is here. It's in this block. In this block, there are 5 consecutive ones. So technically speaking, Rn
of this particular instance, or rather R21, pardon me, of this particular instance is equal to 5. So when I say this particular instance, I'm talking about a Bernoulli process, being modeled under a certain sample space. So there are sample elements involved. The particular Bernoulli process or outcome that I have written down corresponds to a particular sample element. So for that sample element, R21 of that sample element is equal to 5. So that's what this max head run random variable means. And now here you can ask questions about the random variable Rn, and it turns out that the analysis of Rn itself is a fairly well, okay, I was planning to give an example here of this, but it turns out that I've done the demonstration on this page itself. So I really not do it here, right? So remarkably, the distribution of Rn is explicit. So I have provided these citations here. At the end, there is a list of references where you can easily go and check out these things. Most of them are links. Some papers are not links, so you'll have to maybe procure them in second-hand ways, but they're still, you can get them. So remarkably, the distribution of Rn is explicit. So if you fix an n, you can actually get the exact distribution of Rn. That is to say, probability of Rn equal to x for any x, that you can get with some difficulty though. So even more, one can argue using what is called as an independent sum of geometric random variables, that the expectation of Rn and the variance of Rn are of a certain form. So this guy here, this gamma is called as the Euler-Mascheroni constant. This is of course pi, but this formation that you see here, it makes no sense. But once you visit this citation, you'll be able to see why at least there is some kind of sense. So you'll understand that once you understand how Rn can be written as a sum of independent geometric random variables with different indices, by the way. So a famous theorem of Gordon, Schilling, and Waterman, there are two sources that I cite here, actually states that the distribution of Rn converges once you remove certain weight parameters, such as this log 1 by p and by q and q and so on, to a particular random variables distribution, which is called as a Gumbel distribution. So the Gumbel distribution is a distribution on the real line, which has the following CDF, which is written here. FWP of y is e to the minus p to the y plus 1. So this is a very famous result in extreme value theory. The reason why this is called extreme value theory is because Rn is the maximum of something, right? Of in this case, the maximum number of consecutive heads. So maximum random variables are very commonly studied under a branch of probability called as extreme value theory. So this Gumbel random variable, along with two others called as Frechet and Weibull random variables, appear very commonly as limits of maximum random variables. So that's a very famous theorem of Fisher, Tippett, and Neadenko. So, right. Now we come to something called as colored noise. And this already looks a bit weird. I mean, how can you talk about sound and on the other hand, color? I mean, how does this work, right? So, well, colored noise, the reason why we call it as colored noise has to do with how, noise has a certain Fourier representation as a bunch of waves and how waves correspond to colors. So I'm not going to be talking about that because that is unfortunately out of syllabus for us, right? So what are the realistic models of noise that can corrupt information arriving over a channel? So let's say you're talking over the phone. What are realistic models of noise that can corrupt what you're hearing? So for example, how can you model a child that's constantly shouting behind the person on the other side and distracting him? So what is a realistic model of that noise? How can you model, say, a motor that is running behind that person? Or how can you model, say, somebody is watching Kyunki Saas Bhi Kabhi Bahu Thi behind there? How can you model that as a noise? We are not able to hear because the serial volume or the lady is shouting too much over the TV. How can you model that, right? So a very common random variable used for modeling noise is the standard normal. So the standard normal is apparently a random variable that has the highest entropy. In some sense, it basically randomizes things the most in some sense. So if you fix the expectation and variance, it's the best randomizer, or it's the best random variable that can model noise. And
what exactly is the model here?
So that I'll explain. I'm going to explain this in this model that you see here, right? So XT is some kind of information. So let's say somebody is speaking to you on the phone. What they're trying to tell you is XT. So what they're trying to tell you is XT. The noise
that is stopping you from hearing what they sort of hear fully is NT. So that would be the child shouting or the motor running or the TV lady blaring, etc., etc. And the output that you hear, whatever you hear, a mixture of what was supposed to be heard and what was not supposed to be heard, is the output, right? So we are trying to model NT here. So what is reasonable NT? So XT and YT could be something else. We will ignore those guys. The important thing for us is NT. And what we want to ensure is that NT is in N01, right? So ideally, we want to ensure that we can introduce patterns amongst noises at various times. So for example, let's say I take a noise like that is a noise, and there is some randomness to that noise, but there is also a pattern to it, because you can make out that there is an amplitude increase and an amplitude decrease. So the point is, how do we model a larger category of reasonable noises? And that is the inspiration behind colored noise. So a colored noise is a discrete time Gaussian process. So I will be defining that in the next slide. But the idea here is that this colored noise should be capable of modeling a large category of reasonable noises. And this is also used as the first type of noise driving stochastic difference equations. So that I will not elaborate upon. I have left a link there, so you can read that.
What do you mean by high entropy? Gaussian random variable has high entropy.
Oh, that entropy is just the amount that, you know, the random variable spreads out in some sense. So once you fix the expectation and variance, so the variance is a kind of measure of spread, right? So the entropy is also a measure of spread in some sense. So the highest entropy is the kind of the highest spread. So the normal random variable provides the most spread for a fixed expectation and variance.
Why would that be ideal for modeling noise?
Because noise should be, well, it should be as distracting as possible. Well, not just that, but also because the normal random variable has certain very convenient properties. So for example, if you add two normals, independent normals, you get another normal random variable. If you take the ratio of two normals, you get another very conveniently modeled random variable. So all these, so the fact that we know so much about the normal, basically speaking, explains why it models noise. So it's mathematically viable in addition to being reasonable, right? I hope that answers your question.
Why are we modeling noise in this manner? I mean, what's the purpose?
No, I mean, we model noise because it occurs in nature, right? So I mean, I don't really get the question. We want to model noise in some way. So we need patterns amongst noises at various times. Like, as I explained, I just made noises to explain it, right? So that's kind of the idea. It's just, we need a model for noise. Stochastic noise, we need random variables that can represent noise in systems.
Okay, thanks.
Right? Right. So, okay, now this, I hope that this talk might go to 2 hours. I'm pretty sure it might. All right. So a short note on colored noise. So a colored noise is, essentially speaking, a stochastic process for which each individual random variable is normal. So that's bullet point number 1. Bullet point number 2 is that each joint distribution of n different time points. So that is to say, if you take t1 less than t2 less than up to less than tn and I prime, that is n different time points, their joint distribution is that of an n-dimensional normal random variable. And if you look at point number 3, the covariance of xs and xt for 2 different time points is given by a certain function k of s comma t. That is called as the covariance function of this colored noise. So k of s comma t can be used to introduce interaction amongst the noise at various time points. So for example, when I say I or something like that, then between 2 different points at which you think that the amplitude is the same, the covariance between them must be high. And between 2 points that you think that the there is no relation between these 2 time points, the covariance between them must be low. Low in magnitude, that is not necessarily as in low as in the negative sign. So if the covariance is excessively negative, it also means they're related. It just means that when one goes high, the other goes low. So that, basically speaking, the covariance is the kind of way to introduce interactions amongst these normal random variables. And a big result, which also explains why normal random variables are so important, is that every possible joint distribution of a colored noise is determined by a choice of k. So k is just a function of 2 time points. You just take s comma t. Why should it be true that every single joint distribution xt1 up to xtn has a distribution that is determined by just k? So why should just why should just a choice of what happens between 2 time points determine what happens between every possible set of n points? So that is a remarkable result, which is fairly difficult to prove. Again, I have attached a citation for it, an MIT document. So this can be proved using some kind of characteristic function technique. So I will not be again going into that in much detail.
When you say KST is equal to 0, it means for all S and T, right?
Yes, KST is equal to 0 for all S and T. So white noise is the kind of noise where it's basically an IID N01 random process because there's no relationship between 2 time points. Okay, so that's just KST equal to 0. Brownian noise is a noise where KST is equal to minimum of S comma T. So I won't be, I mean, this is kind of difficult to understand when I just state it as a mathematical statement. On the next slide, there'll be some photos. So
also, what do you mean? Can you explain the second bullet point once more?
The second bullet point, do you know what an n-dimensional normal random variable is?
Not sure. Is it the product of?
No, it's not. It's not. So let me give you a quick idea of what that is. So a n-dimensional normal random variable is basically speaking, if you take, so let me underline this here. So when I bring it here, so let's say y1 up to yn be independent n01 random variables. So the yi are IID n01 random variables. Okay, any linear transformation. So let's say you fix a matrix that is an n cross n matrix. So this is a fixed matrix. So it could have, it must have fixed entries, not random entries. It has fixed entries like 1, 2, 3, -1, and so on. Any matrix or any linear transformation of IID N01 random variables is called as an n-dimensional normal random variable. So, xt1 up to xtn is an n-dimensional normal random variable if it's a linear transformation of some of a vector of IID N01 random variables. I hope that's clear. Now,
each of the XTIs are linear combinations of normal.
So each of the XTIs are linear combinations of normal random variables, right? Of IID normal random variables.
Okay, thanks.
Yeah, welcome. So we will now move to pictures. So we will look at what exactly this covariance function does, right? And this pink noise, the last thing that I mentioned here, is a very convoluted definition. You might be like, oh my God, what's going on here? Well, if you look at h equal to half, sorry, if you look at h equal to, yeah, that's right, half. If you look at h equal to half, then you'll notice that KST is actually equal to minimum of S comma T. So pink noise for h equal to half is basically speaking the Brownian noise. But pink noise is technically considered for h equal to 1/4. So that is to say, it has a covariance function that is less than that of Brownian noise. So what's the idea here? The idea is that white noise, there's no relationship between noises at different times. Pink noise, there is a relation, probably not as much as we think. Brownian noise, there's a huge relationship. So you'll see a very good big relationship between noises at different times, right? And this will be shown in the diagrams. So in this diagram, this sample should just refer to time. So this just means time 1, time 2, and so on. At the top is you have the white noise. So this is white noise. This is pink noise with h equal to 1/4. And this is brown noise, Brownian noise, if you like. So if you look at white noise, it's got like this uniform profile, right? It just looks like each guy is acting independent of the other time point, and it either goes up or down based on whether that particular normal random variable value is positive or negative. So it's just independent. If you look at pink now, on the other hand, there's some kind of relationship. So it doesn't look like it's utterly random. There is some kind of ordered structure to it, but there's still too many fluctuations in the middle. There's still way too many fluctuations in the middle. If you look at the Brownian noise though, there's just far too much structure. For example, it looks continuous, and it is in fact continuous. Yeah, this is a picture of a random path. This is a picture of a random path. So you take a particular omega in small omega, and that will give you a path, and that path is being plotted here. So the x-axis represents time and the y-axis represents nt, where t is that particular time, right? So if you look at Brownian noise, it's extremely well organized, really well organized. So Brownian noise is often used in systems where the noise is kind of continuous in some sense. So like the hum of a generator or something like that. Whereas white noise, I mean, I like to think of it as when I was in second standard, and you know, we had kids, we had free period after free period. In every free period, the amount of kind of like the things that would happen in our classroom used to be crazy, because two people on the corner gossiping, two people trying to decide anti-girl measures and stuff. So there was this kind of absolute mayhem in the class, and there was no pattern to it. Nobody knew what would happen at what time. Randomly people would start shouting, randomly kids will fall quiet, randomly there'll be a fight and people will start cheering. So I think of white noise in that way. Well, pink noise can be thought of as a slightly more organized class, maybe when I was in class 7 or 8. So, right. Now we move to what are called as autoregressive processes. So autoregressive processes are processes that try to model themselves based, that basically try to predict the future using the past. So if you look at the definition, it's yt as summation I equal to 1 to p, some ci yt minus I plus nt. So nt here is y